In our last video, we learned about nuclear reactions. We said atoms, if they're not happy, if they have too many neutrons, not enough neutrons, they can fall apart, just spontaneously, just sitting there and go poof, fall apart into 5 different types of particles. We had alpha, beta, positron, neutron, and proton emission. And what we're going to do in this video is we're going to practice doing some of those nuclear balancing reactions. I'm going to focus primarily on the reactions on the left here, so I'm going to zoom those in. And I really encourage you to stop the video, write all those reactions down, and see if you can figure out all those different question marks that are in there. If you remember, our technique is to balance mass number and balance atomic number. So a good time to pause now and try those out and see if your answer agrees with my answer. All right, you're back, which means I assume that you did it. We're going to balance mass number and atomic number. Remember, the arrow kind of acts as our equal sign mathematically. So 11 equals 11 plus, oops, not plus 11, plus 0. And on the bottom, we get 6 is equal to 5 plus y. And that means we've got a 1. And that's a positive 1. And then we've got to figure out what particle has a 0, 1. We can't go to the periodic table because all the things on the periodic table have a mass number greater than 1. Or 1 or greater, because they have protons or neutrons. So what we're saying is this thing, with a mass number of 0, has no protons and no neutrons. And if we look back, 0, positive 1 is a positron, which we usually represent like that. And so this question mark becomes 0, 1, E. And like I said, I really like us to have that positive 1 down there, just to really indicate that, yes, we did mean a positive 1. So let's look at this next one. We've got sulfur 35 making something plus 0 minus 1 E minus. Now what's the 0 minus 1? If you remember, that's your beta particle. We could have just as easily, I love it when this thing scrolls randomly, we could have just as easily written that as a beta right there instead of 0 minus 1 E, but we wrote 0 minus 1 E in this case. We're going to balance mass number and atomic number. 35 is equal to something plus 0. And there our x is going to be 35. And we're going to balance atomic number. 16 is equal to y plus minus 1. So very tempting to say 15. But if I take 15 and I add minus 1, I get 14. And so in this case, I've got to do 17. And so 35, 17, we've got to find element 17 on the periodic table. And that is good old chlorine. So we say that sulfur 35 undergoes 0 minus 1, again it was beta, undergoes beta decay to form chlorine 37. And our next one, we're actually finding the thing that's falling apart, but it's okay, it's no different whatsoever than what we did in the previous ones, except our x is over here. So we say x is equal to 90 plus 0. And so we get a 90 over here for our mass number. And we get y is equal to 39 plus minus 1, which is a 38. And we go to our periodic table, which is off to my left here. And element 38 is strontium. And so we find that strontium 90 undergoes, again, 0 minus 1 is beta decay to form yttrium 90. Last one on this page. Bismuth 210 is falling apart, forming something plus 42He. And if you remember, 42He is the same as an alpha particle. So what are we going to do? Balance mass number and atomic number. 210 is equal to x plus 4. Well, that gets us 206. And then 83 is equal to y plus 2. And that is an 81. We go over to our periodic table and we find that element 81 is Tl, so it's thallium 206. So bismuth 210 undergoes alpha decay to form thallium 206. So there's some reactions that we can balance if it's written as a reaction. But what if it's given to us as a word problem? Well, what we want to do is if we're given a word problem involving these kind of things, we want to turn it into a reaction so that we can balance the way we've just been practicing. So mercury 188, remember that 188 is my mass number. Mercury Hg if you find it on the periodic table, and it is element number 80. And it's going to emit a positron. Where is that positron going to go? It's going to go before the arrow or after the arrow. Emit means it's producing, it's making. And so that positron is going to be a product. Now, I'm just going to give it to you here. The positron had a mass number of 0 and an atomic number of +1, and we usually called it an E right there. And then we got to figure out what else it turned into. We're going to say 188 is equal to 0 plus, right, 188. And 80 is equal to 1 plus 79. We find element 79 on the periodic table, and that is gold. So all the people out there who tried to do alchemy over the years, turn one element into another element, they usually were trying to make gold. What they should have started with is some mercury 188, because it spontaneously turns into gold. Now, don't go out and try to collect a bunch of mercury 188. You're not going to find a whole lot of it out there, and you're not going to be able to make any money off of it. But it will spontaneously turn into gold over time. We'll talk later in one of the videos about how long these kind of things take. Not this one specifically, but are these kind of reactions fast? Are they slow? Is it happening in front of my face, or is it happening over a long period of time? And we'll see different examples of that going forward. Here's a problem for you to try. What type of particle does cadmium-119 emit if it turns into indium-119? Good time to pause, try the problem out, and see what you get. Okay, so you're back, which means I assume that you figured that out. So cadmium-119, is that going to be a reactant or a product? Well, it's emitting. It's sitting there doing something, so that's going to be one of our reactants. And we find cadmium on the periodic table. It is element number 48. It's always good to write that atomic number down because we're going to need it for balancing later. We're emitting something, so nothing else goes on the left-hand side of the arrow, goes on the right-hand side of the arrow. We don't know what we're making, but we know we're also making indium-119. And so indium looks like that. It is element 49. And then we just have to do our mass number and atomic number balancing in order to figure out the answer to this one. 119 is equal to x plus 119. X is going to be 0. So our question mark is going to have 0 mass number. 48 is equal to y plus 49. It's going to have a -1 as my atomic number. 0 minus 1, that was a beta particle. And so we're going to say, hey, these guys emit a beta particle when cadmium-119 turns into indium-119. Now, it turns out that not only does nature make these lovely radioactive isotopes, we can make them in the lab as well. And we can run reactions in these little nuclear accelerators. You probably heard that term before, where we smash atoms into each other at really high speed, like near the speed of light, which is crazy fast. I mean, light goes around the Earth several times per second. That's how fast light is. And we're accelerating these particles to near the speed of light, crashing them into each other, and making new things. Now, if we're crashing two things into each other, we're reacting those two things, we're going to have at least two things, and usually only two things, on the left-hand side of our reaction. So what I'm going to do as a first example is I'm going to take some helium, and I'm going to crash it into some boron. You don't need to know how to do this or predict these reactions, but you do need to know how to balance them if I give you one. So we've got some helium crashing into some boron. What does it make? Well, I'm going to tell you it makes a neutron, 10N, and let's figure out what else it makes. That's not a very good question mark. There we go. Let's figure out what else it makes. We're going to balance mass number and atomic number just like we've been doing the whole time, but now we have two things on the left-hand side, but that's okay. It's the same as what we've been doing. We get 4 plus 10 is equal to 1 plus x. Right, so we've got 14 is equal to 1 plus x. X has got to be equal to 13. On the bottom, atomic number 2 plus 5 equals 0 plus y. Y must be equal to 7. And so we get number 7 on the periodic table is good old nitrogen. And so when we take helium 4 and boron 10, smash them together, we make a neutron. and nitrogen 13. So that's how we can balance nuclear reactions when we are producing them, when we're reacting to different nuclei to make something new. Here's a couple more examples. I'm going to blow them up here. Good for you to pause the video, try these out, and see if you get the same answer that I do. All right, balance mass number and atomic number. 131 plus 1 is equal to 132. On the bottom, we're going to balance the atomic number. Oops, helps if you write down the right number. And that's going to be y plus minus 1. So on the left, we have 52. And so that's got to be a 53 there, because 53 plus a minus 1 is 52. Element number 53 is iodine. And so we can take tellurium-131, smash it together with a neutron, forming iodine-132, and 0 minus 1 is a beta particle. Our one on the bottom here, same thing, 4 plus 27 is equal to question mark, or x, plus 1. Right, 4 plus 27 is 31 is equal to x plus 1. And so x has got to be equal to 30. And then on the bottom, 2 plus 13, that's 15, is equal to y plus 0. So 15 is equal to y. We get 30, 15. You find element 15 on the periodic table. It is phosphorus. So you smash together helium-4, aluminum-27. You get a neutron and phosphorus 30. So balancing these reactions, very, very similar to balancing them when something's just decaying all on its own. And there's that different language there. When something decays, it's just sitting there by itself. It emits something, so you usually have one thing on the left, usually two things on the right. But here we are smashing these things together. We are colliding them. Helium is collided with aluminum to form a neutron and phosphorus. All right. On this slide, it's just some information that I want to give to you. You don't need to know this. This isn't going to be on a test or anything, but I think it's a very interesting periodic table. And what this periodic table shows us is the number of stable isotopes that exist in nature for each of the different elements on the periodic table. And so we can just pick an example over here and we look at beryllium. Beryllium is orange, which means it only has one stable isotope that exists primarily on the face of the Earth. Well, that's kind of interesting. Why is there only one for beryllium? Well, I don't know, but let's look at the other. Chromium is a kind of light blue color. Actually, it's more that green color, sorry. It's that green color. And so there's 3 different stable chromium isotopes that exist in nature. And as you can see, it varies a lot. Some of them have 7 or more, and some of them have 0 in red. What does it mean to have 0 stable isotopes? It means that all these guys down here that are in red, if you leave them sitting there long enough, eventually they're going to disappear. They're going to spontaneously radioactively decay into other things, other elements, because they are not stable. Some of them do it very, very quickly, and some of them do it over a longer period of time, but none of them are stable. My favorite is this one in the middle of the periodic table that's not stable. It's technetium. It's just there in the middle of all these other stable things, but not a single stable isotope of that exists, and it's also my initials, which is why I like that. So, why do I bring this table up? I bring it up for one reason. Well, 2 reasons. One, it's just interesting all on its own. But 2, do you notice any patterns when you look at the colors on here? Like, look here. We've got an orange column, then we've got kind of a blue column. We've got an orange column and a blue column. We've got these columns where only 1 or sometimes even 0 stable isotopes exist. Right next to these columns where lots of stable isotopes exist, like ruthenium here has lots and lots and lots of stable isotopes that exist. But on either side of it, there's something that has 0 and 1 stable isotope that exists. Why is that? Well, if you notice, all these ones that have lots are all even numbers. And it turns out nature always loves things in pairs. Nature loves to pair electrons. Nature loves to pair protons. And so elements that have pairs of protons in them always are more stable than elements that don't. And so all these things with different even numbers of protons are more stable than the things with odd numbers of protons. And in fact, it works for the neutrons too. Those elements that have an even number of neutrons are more stable than those elements that have an odd number of neutrons. And it's just an interesting fact, not going to be on a test, not going to be even talked about really anymore, but very interesting to understand that nature really likes things in pairs. All right, what did we learn? We learned about how to balance nuclear reactions, whether something was decaying, just sitting there by itself, forming something, or being collided, bombarded with other things, two things reacting to form some products. Thank you. Have a good day.